models, computer vision, and advanced audio processing. He's also dedicated to making AI robust and very, very reliable. He notably led the development of Sabian 125M, which is Nigeria's first decoder-only foundational language model that is capable of performing NLP tasks and generating text in 8 Nigerian languages. He has showcased his ability to innovate within constraints and achieve remarkable performance, thereby pushing the boundaries of natural language. Jeffrey's outstanding work significantly outperformed GPT-4 and Llama 2 13D on Nigerian language benchmarks, just so you know. So you know how exciting it is to have him facilitate this particular workshop. Beyond research, he specializes in full AI lifecycle with a wealth of experience in designing and evaluating tailored AI solutions that automate complex domain-specific tasks across various industries. He's driven by a vision to create contextual, cost-effective AI and robotics technology specifically for Africa and healthcare, given that he is a medical doctor as well. Right, ladies and gentlemen, please do well to put your hands together for Jeffrey Otoibhi as he takes over. Hello, Jeffrey. Over to you.
Hello, everyone. Good evening. It's an honor to be here this evening. I'm glad to see that everyone is excited for this session. It's going to be very informative. At the same time, might be complicated for a lot of people here because of the mathematical concepts involved. All right. So I think Sam, thank you for introducing me. Right. Zion, thank you for this opportunity to share in your work of building the next generation of AI people experts in Nigeria. So let's jump into it. Let's just jump into it. Before we start this presentation, I would like to give a disclaimer that this might be a little bit tricky for a lot of people here, especially if you do not come from a mathematical background. But nevertheless, I would do my best to make it work. All right. So, but if you have any questions, any comments, I would like to hear it, and I would like to take them as I move on with this lecture. So, can everyone hear me? Hello, can you guys? Okay, good.
Yep.
And you guys can see my screen, I'm guessing. So I'm just going to start. Okay. I will skip the intros. I'm going to skip the intros now because we honestly do not need it. Okay, so this is going to be the course outline. First, I will give a refresher on neural networks. Then we would start with the Transformer Foundation, which is the fundamental unit of the LLMs that everybody know now, the large language models that everybody know now. Then I'll talk about the different transformer architectures, talk about how the decoder-only type of transformer became the best kind of transformer model and the most used transformer architecture in the world currently that has led to the development of all the big models that you know, ChatGPT, Gemini, DeepSeek, Mistral, and the rest. Then we would break down each of. We will then we will talk about the innovations that came after we got a breakthrough in 2022 after the release of ChatGPT 3 and 3.5. We'll talk about the innovations that have occurred since that time, 2022, given that people would like to scale the transformer model to be faster and to be smaller. So we'll talk about all these things today. It's good, like I said before, it's going to be quite complex, but I will do my best to break it down You can always reach me after this lecture to if you have any questions, but I would like to take questions during the sessions too. So if you have any questions, just write them down and prepare them for me, and I'll take them at the end of the class. Okay. So let's start with the brief on neural networks. I'm sure you guys have been already. You guys have already been doing statistical and deep learning last week, so I won't spend so much time here. But I would say this: there are different deep learning architectures that have arisen since the advent of the term AI, and the different architectures in the past were used for specific types of modalities. So I would explain further. Now, for tabular data, everyone is familiar with tabular data. In the past, we would strictly use a linear model or a statistical model or just a multi-layer perceptron, which is like just a normal neural network. Then for images, we would use a convolutional neural network, right, in the past. Then for text generation, for text classification, sentiment analysis, and all those things, we would usually use something called the recurrence neural network, which is an RNN, or an LSTM, or a GRU. And you can see the images I've put up. You can see it on the screen right now. So these are the things we usually use for text generation. The same also applies for audio generation and audio classification. The reason is because both audio generation and audio classification and text generation have the same format. It's like a sequence of words or a sequence of spoken words that follow each other through time. So it's like a sequence. And because it was like a sequence, we would use a recurrent neural network to model that sequence to sequence or word to word generation of the next word, right? In quotes. Now, we started out with a recurrent neural network. This was the most basic form of architecture that modeled audio generation, classification, text generation. But we realized quickly that this particular architecture suffered a lot. It suffered from something called vanishing gradient. If you're familiar with the way deep learning models work, I'm sure you covered some of this last week. I'm sure they mentioned that they mentioned something called forward propagation and backward propagation. Now, when information flows through the model, we would usually get a loss given the ground truth. If I'm confusing anybody, please let me know. It's very important that you get this. All right. So, in essence, the vanishing gradients made these recurrent neural networks not to learn as much as possible. Oh, don't worry. Okay, I'll try to go slow. So, like I said before, for sequence to sequence generation, we had a model architecture called recurrent neural networks. We used it to model audio generation and text generation. Now, we started out with a simple recurrent neural network, which is the most basic. The most basic. You will see an RNN on the right here. You see an image of something called an RNN that has an H in it. It was the basic unit of, or the most primitive architecture used to model sequence generation. Right? But it suffered from something called vanishing gradient. I will try not to explain so much, but this vanishing gradient made this model architecture not to learn a lot. It made it not to be so robust. Now, because of these vanishing gradients, researchers came out and developed something called an LSTM, which means long short-term memory, right? Now, for this architecture, they embedded like a memory unit in it using different gates. If you will see in the image under LSTM, there's a forget gate, there's an input gate, and there's an output gate. Now, it's with this gate that they were able to work against the vanishing gradient problem that existed for the recurrent neural network. So LSTMs performed better than the recurrent neural networks. However, they still suffered from the similar problems, the same vanishing gradients, and they couldn't model long context generation or long generation. So for text requiring maybe 1,000 words, they couldn't model it that far because they kept forgetting and became repetitive. So this led to the development of the transformer architecture that we all know now, which is used in LLMs. Now, the transformer architecture brought a lot of things to the table. First, there was no vanishing gradient anymore. Why? Because it removed recurrence. It was because of the recurrent nature of the recurrent neural network and the LSTMs that they couldn't learn so much. So after the transformer came out, they introduced something called parallelism. And so in parallelism, we could put all the sequences at once, and the model will learn next and produce the next token or the next word. So they solved the vanishing gradient problem, and so they became more robust. They became more capable in their abilities to predict the next word or to generate the next audio sound and so on and so forth. Now, this transformer architecture also introduced something very important, which is called self-attention or an attention mechanism. Now, why is an attention mechanism important? After the linguistic researchers studied so many texts, they realized that words in sentences have a relationship with each other, right? So when I say I am going to the market today, or as you can see in this example, I am a student, there is a strong relationship between the word I and the word student, right? Because student in this case is I. So I am the student, right? So there's a very strong relationship between words, right? And they notice this exists for all words in the English language, and how a particular word in the English language could mean different things based on the context in which it is found, right? So what was a typical example? The word like, for example, can be used with to refer to a person, or liking a food, or liking a particular action, like liking to play, liking football, liking basketball. So it means that the meaning of like changes according to the context in which it is found. So because of this fundamental pattern in natural language, they came up with something called an attention mechanism. And what the attention mechanism does is it tries to calculate the relationship between words in a given context. So when it is given a sentence, it will try to calculate, okay, which word is strongly related with another word? Which word has no particular weight when it comes to the meaning of this sentence? So, for example, some words do not carry any meaning in a sentence. So, if you look at this sentence, I am a student, you will see that the article a, it doesn't really confer any meaning to this sentence. We can do without it, and we will still make some sense of the sentence. So, I am student, it will still make a lot of sense. So, the attention mechanism was created to downweight the words that did not really carry so much meaning, and to upweigh the words that carried so much meaning and had relationship with other words in a given text. That way, it learns how to provide some contextual understanding to every input sentence that is passed to it. Is everybody following me, or have I lost some people? Hope you keep crying. Stop crying. No, it's not the end of the world. Don't worry. Just know that Jesus is alive. This is not the end. The life will continue after this. But the point is, the attention mechanism was created to learn the relationships between words in a sentence. You have to remember this. That is the essence of attention. So without attention, it could have been incapable of us to calculate the relationship between words in a given sentence, to also determine the meaning of a particular word given the context in which it is found. Like I've said, the word like can mean different things when used in a context. I like food, I like football, I like food, I like my mother, I like the market, I like my TV, I like sleeping. So you can see that the word like is forming different relationships with different words according to the context in which it is found. So that's another thing that the transformer architecture introduced. So the first thing is it removed the recurrence that you would find in the recurrent neural network. It brought in self-attention that tries to connect words together to get better meaning of the word in context. Then it also captured longer range. So I remember I said that for the recurrent neural network and the LSTMs, they couldn't really capture they really couldn't continually predict the next word as the sequence grew. So let's say they would do well with just 10 words or 10 sentences that had just 10 words in them. But by the time you try to make them predict on 1,000 words, right, or 20,000 words, we start to see that they perform woefully. They don't make any sense. So with this transformer architecture, we were able to capture more long range dependencies. So it doesn't matter, even if you give it a story and professor was written at the beginning of the story, and professor was also mentioned at the end of that story, it will capture the relationship between those two professor words, right? Because it can now calculate the attention between all of them. It can calculate the relationship between all the words that is passed to it. This is one thing that the LSTMs and recurrent neural networks failed to do. So again, I repeat, the first thing it introduced was it removed recurrence from the model architecture, which you would see in recurrent neural networks. It introduced attention mechanisms, and this attention mechanism makes it good for models to determine by themselves the relationship between words, to determine the meaning of a word given a particular context in which it is found. It also helps the model to downweight any word that doesn't really confer any meaning to a sentence. Right? Look at it like a compressing algorithm. We are trying to reduce the weight of words that don't really affect a sentence so much, and we're trying to upweigh the words of words that actually trying to upweigh the words that actually carry a lot of meaning. So that is exactly what the attention mechanism is all about. I will show you the basic formula for the attention mechanism eventually. If you like mathematics, you would like it. Hope I know you don't like mathematics, so you are going to hate it. But anyways, I'll be praying for you. But let's move on with this lecture. Okay, so now before I go into the core detail of the transformer architecture, like we mentioned here, before I go into the full detail, I would like to talk about something very important called tokenization. Now, before any input is passed to a transformer model, by input in this case, for simplicity, I'm going to stick with text generation, right? So before an input text is passed to a transformer model, you can't see my screen. Okay, let me try and okay. I hope everyone can see it now. Okay, good. So for simplicity, we are going to stick throughout this discussion. We are going to stick with text generation, right? But remember that LLMs can be used for both images, text, audio, any kind of data they can be used with an LLM. But for this discussion, I'm going to stick with text because it's easier to understand. Now, before we go strictly into the transformer architecture itself, I would like to talk about tokenization as simple as I can, the best way I can. Now, before an input text is passed to a transformer model, it goes through a process called tokenization. So what is tokenization? Tokenization is a process of simply breaking, let's say, a sentence into words or subwords, and then converting those subwords to an integer using a lookup dictionary. So imagine that we had a dictionary, if you're familiar with Python or any programming language. Imagine we had a dictionary that contained 1,000 elements, and you know a dictionary carries both a key and a value for each of those elements. And so imagine that a word, let's say the word like was number 1 and the word play was number 2 in that dictionary. So what tokenization would do is that if you pass it an input sentence, it will first break it into subwords. So if you look at the diagram on the left, you see an input sentence, hello, how are you today? And you see how it goes through the steps of tokenization. It is broken into words or smaller words, so into a list. So you can see that the final output is the last item below. You can see that it has broken the text hello, how are you today into hello, how are you, CD, and then A, right? I will show you a second example in a minute. This is another example. This is as simple as it can be. On the left, you would see that we have a long sentence, and this process of tokenization breaks it down into words. In this case, just into words. So grew a pretty little fir tree. Now, after the sentences are broken down into words or subwords, they are each of those words or subwords are converted into a number, which is an integer. So if you look at the right image here, you would see machine learning archive. And after tokenization, it's broken down into machine learning archive. So this is a simple word tokenization system. Now, each of these words are then converted into a number. So you can see that the word machine is converted into 2, the word learning is converted into 4, and the word archive is converted into 8. And the exclamation mark, if you notice very well, you see that the exclamation mark is also converted into a number 12. So every single word, every single subword is usually converted into in an integer format before it is passed into a transformer model. Now, why is this done? It is because models work better, they don't work better, they work only with numbers, right? They can only work with numbers, they can't work with text. They don't understand text, they understand the number representation of that text. So if it means that if you can create a dictionary that holds the identity or a digital or a number representation of every word that we can find in the English dictionary, it means I can convert any word into a number. I don't know if that makes sense. So if there are 1,000 words in the English dictionary, I can simply just create a lookup table that has 1,000 words with their corresponding number representation. So this is the process. So an input text is broken down into words and subwords. After it is broken down into words and subwords, it is then converted to its integer format. Why? Because models only understand numbers. They don't understand text truly. They only understand numbers. This is very important to understand. Is anybody confused at this point? Because this is really very important to understand. Okay, so I'll go on. Everybody's happy now. That's good. Okay, now let's talk about the transformer architecture in proper now. Now, I will give a general overview of the transformer architecture, then I will break this architecture into its fundamental parts. Then we'll discuss the fundamental parts. Now, you can see 2 diagrams here in this image. One called GPT architecture, and another one called GPTG architecture. Never mind all those, they're just names. Let's focus on the GPT architecture. Now, the basic transformer block consists of an input embedding. I will explain what that means. A layer normalization, an attention mechanism layer, another layer normalization, a feed-forward layer, a layer normalization, a linear layer, and a softmax layer. Now, I'm assuming that last week you were taught what neural networks look like. That is my assumption here, right? Because it'd be practically impossible to explain every single thing in this class, but I will do my best, like I said. So usually, after sentences are tokenized into IDs, they will be passed into this input embedding layer. Now, this input embedding layer will transform that integer format of every word into a vector. After it transforms into a vector, it is going to be passed upwards like this. till we get to the output prediction layer at the top here. So again, tokenized words are converted to integers. Those integers are passed into this input embedding layer, and then it starts to forward propagate those vectors up this transformer block till we get to the top. So fundamentally, the transformer block consists of an input embedding layer here, right? A layer normalization layer, a maxed multi-head attention layer. I would explain what this means. Another layer normalization, a feed-forward layer, and then basically an output layer at the top here. Right? So we will start by explaining each of these as we move forward now. So let's start with the embedding layer. The picture on the left clearly shows it beautifully how this is represented. Now, remember when I said that we have an input text, so you can see that there's an input text here. The fox jumps over dog. Now, just for the sake of this class, imagine that a word is a token. So the word fox is a token, the word jumps is a token, the word over is a token, the word dog is a token. So the first thing that happens again is that each of these tokens are converted to an integer format. So you see here that fox is converted into 2, jumps is converted into 3, over is converted into 5, and dog is converted into 1. Now, these IDs are then passed to the embedding layer. This is the embedding layer down here, right? Or this is the embedding layer down here. So you can see weight matrix of the embedding layer. This is the embedding layer down here. So the embedding layer is a simple matrix. For the people familiar with matrices, this will be easy for you. For people not familiar with matrices, this will be very hard for you. But unfortunately, there's nothing I can do about that at the moment. So the embedding layer is simply a matrix, right? That can convert each of these IDs to a vector. So when 2 meets with this embedding layer, it will be converted to a vector. So let's follow it. So you can see that the number 2 is highlighted here, and that number 2 belongs to the token fox. So after fox is converted to an integer, we go to this matrix and make a lookup at that position 2. Right? So the first one here is position 0, position 1, position 2, position 3, position 4, position 5. Right? Now, since the integer format is position 2, we will simply go to that embedding layer and pick out the vector at position 2, which is this vector here, 1.2753 minus 0.201, and so on and so forth. We will pick it and then we will put it in our output. Then we go to jumps. It is position 3, right? So again, we'll go to our embedding layer, which is like a lookup table. We'll count 0, 1, 2, 3. So this is the vector representation of the integer 3. We'll pick it out again and we'll put it in our output. So you can see that in our output here. We will go again. Over as an integer 5. We'll go to lookup table. We'll pick out the vector at that position 5. So 0, 1, 2, 3, 4, 5. So you can see this is the vector representation for the index 5. We'll pick it out and then we'll put it here. Dog has an integer value of 1. We'll go to the lookup table 1, which is this. We'll pick it out and we will put it here. So you would see that at the end of this, embedding layer, the output of this embedding layer, you would have converted a single integer to a vector. So for every integer which corresponds to a particular token, we would have converted that integer to a vector. So you can see here that we had 4 elements in this list here. And here we also have 4 elements in this list. The only difference is that we have moved a scalar quantity, which was an integer value, to a vector quantity, which is like a range of continuous values. Is anybody confused at this point? If you are confused, please. Okay, so I'll try to summarize. Now, the first part of the transformer block is called an embedding layer, right? As you can see here, that's the first part. What the embedding layer does basically is that it converts the integer representation of every token after tokenization into a vector space. The way it does it is by simply looking up that integer value in a matrix box. So if you look at the image on the left, you can see that the input, there's an input text called fox jumps over dog. Good, that's a good question. What happens to the first index? 0. If you look at the input text, you would see that there is no 0 in the input text. Remember, we converted each of these tokens to a number. Fox was converted to the number 2, jumps was converted to the number 3, over was converted to the number 5, dog was converted to the number 1. So in this input text, there's no number 0. Right? So for the first input text, it is the position 2, right? So we'll go to our lookup table, which is the embedding layer, and we will pick out the vector at position 2. Now, in Python, or in this case in AI, the first element is always a 0. The index of every element in a list is always a 0. So every list will always start with index 0 and move to 1 and to 2. So it means that in this matrix, the first element is index 0, the second row is index 1, the third row is index 2, the fourth row is index 3, the fifth row is index 4, and the sixth row is index 5. So when the model encounters the number 2, it will go to that row 2 and pick out the vector there and then drop it in an input box. It will go to the next word, which is jumps, which has been converted to the number 3. It will then go again to the embedding layer. Look out for the row 3. So this is row 1, row 0, row 1, row 2, row 3. It will pick out this row 3 and put it again in the output. It will go to the next word, which is over, which belongs to row 5. It will go to the embedding layer, which is a lookup table, pick out that layer 5. So row 1, the row 0, row 1, row 2, row 3, row 4, row 5. It will pick it out and drop it here. So we are basically converting those integers into their vector representation by looking at the index in this embedding layer, which is just like a lookup table. So if the next word in this input text was converted to 0, right? We would simply go to this embedding layer, look up the row 0, we pick out the vector at row 0, and then append it to this our output box. So what the embedding layer does is converting the integer to a vector. That's all it does. And the way it does it is by looking at a lookup table, which is like a matrix, and picking out the row for that particular index and using it to represent that token. Is anybody still confused? If you are confused, you will send me a message later. Okay, I think I've explained it good. Okay, so that's all about the embedding layer. Now let's go to the next thing. Now we have converted, let's go back. We have converted every single token here to a vector representation. But the problem now is that we've not accounted for how the words are ordered. So for example, we know that in English language, we would typically start a sentence with a subject and end the sentence with an object. Now, when reading an English sentence, we already know this in our brain. We know that, okay, this is how the word is supposed. This is how the words are supposed to be ordered. You cannot put an object at the middle and put the subject at the end. We need to start with a subject, then a verb, then we end with an object. We know that already. So there's an order to the way we write, right? So it means that we also have to mathematically represent this order, which we find in language, in our transformer model. Now, the way we did that was we came up with a system called positional embedding. If you see this picture here, you would see that this is the input embedding layer we just spoke about, and there's something on the left here called position embedding. Now, what this position embedding does is that it adds extra information. It adds extra information to these vectors we have gotten here, all these vectors, which were the output of the embedding layer. It adds extra information to that. What is this extra information? It adds extra information about the position of that token in the input sequence. Right? So just the way your brain when you read an English sentence, you know that a subject is supposed to start the sentence, and then followed by a verb, and then followed by an object. We have mathematically represented that pattern in these models by using something called a positional embedding layer. What this layer does is that it will just add more information to each of the vectors to provide the model with an orientation as to how the words are ordered. So think about it like this. The simplest system is we'll just tell the model that, okay, fox is at position 0, jumps is the next word after fox, which is position 1, over is the next word after jumps, which is position 2, and so on. That's the simplest way to think about this. We are giving the vectors more meaning by providing the order in which they occur in the sentences that are passed to the models. So that is what the positional embedding does. So if you look at this diagram, you would see that this is the input embeddings, right, at the top of the image. Now this is the output of the embedding layer, and this is our positional embedding layer that has generated this particular vector. So we would, at the end of this particular layer, we would have added the output of the positional embeddings to the input embeddings. Again, this positional embedding layer just carries information about the order in which words occur in text, right? That's all it does. It is just there to give more meaning to the orientation of words and the position of words in sentences. Is anybody confused? Right? So you would see here that we have, this is the embedding of the first token, and this is also the embedding of the third token. And you would see here that we are using 1.1, 1.2. So 1 here represents first token. So 1.1, it is vector dimension 1. The numbers after the dot are the what's it called, decimal. So the decimal numbers represent the dimension in which we are adding. So while the first number, which is the whole number, represents the position of the word. So in the first token, you see that the whole word there is 1. In the second token, it is 2. In the third token, it is 3. In the fourth token, it is 4. So this is like the simplest way to explain this. We are giving the input embeddings more meaning by providing information about the position of that word in a given sentence. That's all. Is anybody confused? Okay, so I'm going to move on. Now, let's talk about the next layer. Now, let's go back a bit because we'll be tracking this from here. So we've gone through the input embedding, we've gone through the positional embedding. Now we are talking about the attention mechanism. Now, this is the most difficult part of, I think it's going to be the most difficult part of this class. But like I explained before, the attention mechanism basically calculates the relationship between words. Okay, so we will get to the layer normalization. We'll get to the layer normalization, right? But I don't want to talk about it now. We'll get to it as we move on. That's a good one. Let's talk about the attention first. Now, like I said before, the attention mechanism just calculates in real time. If you give it a sentence, it will calculate the relationship between words. It will downweigh the words that don't give the sentences any meaning and upweigh the words that give the sentence more meaning. Right? How do we do this? Let me explain how we do this. Let me see if I have a better image for you on how to do this. Okay, so let's see if I can use this. How can I use this? No. Okay, let's start with this image. So if you look at the image on the right, right? So let's look at the sentence at the base. I am a student, right? So now we track it through the first arrow to the next level. Imagine that is the tokens being converted to their IDs. And let's track it up again to this level. That's the token being converted to a vector representation. At this point, we will calculate the relationship between each of these words and come up with a weight. By calculating the relationship between these words, we will come up with a weight for all of them. Now, if we add up all the weights, they must always add to 1. So in this case, 0.5 plus 0.3 is 0.8, then plus 0.1 and 0.1, that's 1.0. So they must always add to 1. So by calculating the relationship between the words, we will arrive at this attention weight, something called attention weight. What this attention weight conceptually mean is we are weighing the words that confer more meaning. We are upweighing the words that confer more meaning and downweighing the words that confer greater meaning. So again, I repeat, in the attention mechanism process, we will calculate the relationship between words and the dependencies between tokens or words in this case. At the end of this calculation, we will come up with something called attention weight. Now, the meaning of this attention weight is that first, all the weights will add up to 1. So we'll come up with a weight for every token in that sentence. And if we add up the weight, you must arrive at 1.0. The second thing is this attention weight will give a higher value to the tokens or the words that confer more meaning and give a lower value to the tokens or words that do not confer so much meaning. So let's look at this case. You see that in this diagram, the attention mechanism after this level has given the token I a weight of 0.5. So it's basically saying the word I carries a lot of meaning. It has also determined that the second token has a very good relationship with the word I, so it has also given it way more meaning. And then for the words A and student, it gave it a weight of 0.1 and 0.1 respectively, right? For some diagrams, these students might carry more weight because they have more relationship with the word I. But this is just for your understanding. It's not like this is the actual weight, right? So at the end of the attention mechanism calculation, you will come up with weights that will downweigh words that don't have any meaning or and upweigh words that actually confer more meaning to the input sentence. I don't know if I'm going to go into the details of how this is calculated, but let's say that, okay, look at this diagram, the one on the upper right. Imagine, so you can see something called hidden states. I'm sure you can see something called hidden states. It's just English language, don't mind them. They want to confuse you. But look at these hidden states as the outputs of the embedding layer that we saw last time. Let me go back. So look at it as this vector, this output vector at the base of this image. Just imagine that the hidden states are those. Now, for each of these vector, right, in this output box from the embedding layer, we will convert it into a key, a query, and a value vector. So every vector in this output will then have a key vector, a query vector, and a value vector. Now, it is this key vector, query vector, value vector that will be used to calculate the attention weight. How does it do it? First, it will multiply the query with the key. Now, by multiplying the query with the key, we will get the attention weight. Let me see how to do this. So yes, so if you look at this example here, you see the quick brown fox, right? So D is a token, quick is a token, brown is a token, fox is a token. Each of these words have been converted into a query, a key, and a value. So Q represents query, K represents key, and V represents value. So this is what is going to happen, and this is where the maths gets really complicated. So I'll try to mention this only once. Right? So this is what really happens. We get the attention weight of the token D, right? We will take its query vector. Remember, we now have 3 vectors for this token D. So we will take its query vector, only the query vector, and then we will use it to do a dot product with the key vectors of every other token in the input sentence. I will say that again. To get the attention weight for the token D, we will take its query vector, sorry, and then use it to do a dot product with the key vector of each of these tokens. So we use it to do a dot product with the key vector of quick, the key vector of brown, the key vector of fox, and the key vector of jumps, and so on and so forth till we get to the last token in the sentence. So we will not stop calculating that thing until we get to the end of the token. So after we have done a dot product of these things, right, it will give us the attention weight for the token D. Now we will move on to the next token. We will take the query of this next token, which is Q2. We will use it to do a dot product with the key vector of the token D, the token brown, the token fox, the token jump. So we just keep using it to calculate do a dot product. Now, by doing a dot product, if you're familiar with mathematics, it's like doing like cosine similarity. So it gives us, by doing a dot product with the key vectors of every other token in the sequence, we are basically saying, like this example, so you can see here we have Q4 multiplying with K5. By doing this dot product, we are basically getting a value that tells us about the similarity between these two tokens, right? So in mathematical terms, the relationship between two tokens in a sequence is formed by doing a dot product. This dot product will give us a value that tells us how similar or related these two tokens are. So that's why we multiply the query with every key, and then we sum it up, right? Now, after we have gotten this attention weight, yes, all this happens during training. Everything happens during training. Now, computers are really fast. I'm only making it slow. I'm making it look very complicated and slow, but computers are really fast, and they do this in a very nanoseconds, right? So, but all these are calculated in real time and calculated during training and also during inference. We will get there. Just bear with me. So what you need to know now is multiplication of the query with the key will give the attention weight. Now, after we get the attention weight, we will multiply that attention weight with the vector token. So after we've calculated the attention weight for the token D, we will multiply that attention weight with the value vector to get the final vector for this token. We will do the same thing for the second token. After calculating the attention weight by multiplying its query with the key of every other token, we will get an attention weight. We will take the attention weight and we'll multiply it with its vector token, and we will get the new representation for the token quick. We keep doing that for every token, so we keep doing that for every until we get new representations, new vector representations for every token in the list. Now, after this calculation, what you would find is that the attention mechanism has calculated the semantic relationship between words, the semantic similarity between words, and has used that to derive a particular weight that determines whether a token is very important or a token is not very important. That's basically what the attention mechanism is about. If you're interested in the formula, this is the formula right here. This is the formula right here. I've explained all these things. So, okay, what is the difference between the query key and value vector? The difference is that we have, how do I explain this? For every transformer block, we have a new set of matrices called a key weight matrix, a query weight matrix, and a vector weight matrix. So you can see here WK is the key weight matrix, WQ is the query weight matrix, WV is the vector weight matrix. Now, for every vector in this hidden state, if I take the first vector in this hidden state and multiply it by the WK matrix, I will get the key vector. If I take the same weight from this hidden state and multiply it with the WQ matrix, I will get the query vector. If I take that same weight and multiply it with the WV matrix, I will get the vector, the value vector. So at the end, each of these vectors in this hidden state will be multiplied with each of these matrices to get a key, query, and value vector. I hope I've answered your question. So in the attention block of the transformer model, you would have three matrices: the W key matrix, which is just for the key matrix, the WQ matrix, which is the query matrix, and the WV matrix, which is the vector matrix. Each vector from our embedding layers output will then be used to multiply each of these matrices to get a key vector, a query vector, a value vector. So if you see in this example, we have 1, 2, 3, 4, 5 vectors, and at the end of the multiplication, we have 1, 2, 3, 4, 5 key vectors, 1, 2, 3, 4, 5 query vectors, 1, 2, 3, 4, 5 value vectors. So every token is multiplied with these matrices to get a key vector, a query vector, and a value vector. After that, we do the attention weight calculation and get a new representation of the vector. Is anybody confused? I guess not. Okay. Yes, so the query, key, and value matrices, these matrices here, this one, this, and this are learned during training. So these three matrices are learned during training. Okay. So let's go to the next thing, which is the attention matrix, the multi-head attention matrix. The multi-head attention matrix is the same as, is exactly the same thing as the attention calculation. The only difference is that instead of making the vector, instead of just making it one vector, let me go back to the embedding layer. So here we have, imagine that each of these vectors were not just, they didn't have, imagine that each of these vectors had more than 3 elements. So this vector here has 3 elements. So imagine this vector had 12 elements, right? And the same with every other thing. Instead of just using the whole vector to calculate attention mechanism, what if we broke the vector into smaller chunk vectors? So let's say, imagine again that instead of these 3 elements vector, we had like 12 element vectors. What if we broke it down into, we broke this 12 element vector into a group of 3 element vectors, right? So in the end, we would have, I hope I'm not confusing anybody, but in the end, we would have, I wish I had a very clear picture. Let me see if I have a clear picture for that. Yeah, it's not so clear. Let's see. So it's not so clear. Okay. It's not so clear. So in the end, we would have, so if we had like a 12 element vector for each of the tokens, so we have a 12 element vector representation for each of the tokens. We can break it down into 4 different, we can break each vector into 4 vectors, and each of those 4 vectors would have 3 elements in them, right? Is anybody confused? So we're basically transforming a 12 element vector into a group of 4 vectors with 3 elements each. So 4 times 3 is still 12. So we're just doing mathematics. Nothing changes. We just did mathematics and broke down a 12 element vector into 4 groups of 3 element vectors. Now, this process of breaking down this 12 element vector into 4 groups of 3 element vectors is what we refer to as multi-head. Why did we do this? We realized that a lot of words have, no, so this is not matrix transformation. This is more like matrix manipulation, right? We are basically on matrix chunking. We are basically taking a 12 element vector and breaking it down into 4 groups of 3 element vectors, right? So it's not transformation. Matrix transformation is what you see in linear layers. Okay, we'll get to linear layers, but if you are familiar with neural networks, multiplying the matrix multiplication, the typical matrix multiplication that you guys have been doing in mathematics is what we mean by a matrix transformation, or a matrix transpose. But typically, it's the matrix multiplication that we refer to as a matrix transformation. This is not a matrix transformation. This is just like a matrix chunking. We are basically chunking a 12 element vector into 4 groups of 3 elements vectors. Right now, the process of chunking this into groups is what we call multi-head attention. So why do we do this? We realize that in every single language, a word does not always mean only one thing. It can mean 6 different things, right? So if we are all familiar with English language, we have words that can be a noun, that can be a verb, that can be an adjective, that can be a pronoun, that can be like 5 different parts of speech, and you are wondering why does it exist? So now, because of all those things, we decided also that instead of just giving every token one long vector representation, how about we break it down into groups of vector representation? Maybe if we do this, we can model the different meanings that these tokens will mean. So we can even model the different parts of speech that these tokens may mean. And when we break it down, we will use this breakdown to calculate the attention between every other token. That way, we can now say, okay, in this part, so for example, let's say a word can be used as a noun and an adjective, right? So now in this vector representation, I broke down a 12-element vector into 2 groups of 6-element vectors, one to represent its noun and one to represent its adjective. When I'm doing the attention mechanism, what will I do? I will take that noun vector, I will use it to multiply every other thing and say, maybe this is a noun, maybe this word in this sentence is actually a noun, not an adjective in this case. Now, by doing the attention mechanism, I might arrive at the conclusion that, okay, it's not a noun. So what will happen is that the attention weight for that will be very low. Then when I take the adjective counterpart and use it to do attention with other tokens in the sentence, I would say, okay, there's more similarity with this particular vector with other tokens in the vector. Okay, so maybe this is more of an adjective in this context than a vector, right? So that way, we weigh one down, we raise the other one up. That's basically what the multi-head attention does. It will take the vector representation of a word, break it down into groups of vectors, and then try to calculate, give the vector representation of that word more complexity to see, okay, which part actually catch, which part did not catch, which part is actually related to other parts of the sentence, which part is not. So we are just basically complicating things. So the noun and adjective analogy is actually the best that they can do at this point, and I hope a lot of you guys are not confused. If you are still confused, say I, and I will have Zion pray for you later. Let's move on. Okay, now we are still going to talk about the layer norm, but let's talk about the feed forward network. Let's go back to our initial diagram of the transformer. So we've spoken about the multi-head attention. We will talk about the layer norm shortly, but we are now talking about this feed forward layer. This is what we're talking about now, the feed forward layer. Now, after we've converted a token to its ID, the ID to its vector representation using the embedding layer, and then we've calculated attention to get a better vector representation of that token, given its context, the next thing we do is we pass it to a feed forward network. And this feed forward network transforms. So this is where you do matrix transformation now. The feed forward network transforms the vector representation gotten from the attention mechanism into something richer. Right? Don't ask me how rich or how is it rich. I don't know, but it just works. Right? Now, this feed forward network is usually consists of 2 layers. So if you see the diagram on the left, you would see that we have a transformer layer which gives rise to the self-attention layer. And after the self-attention layer, we'll get a new hidden state. Now, this hidden state is then passed into this feed-forward network. So look at the feed-forward network as like a projection layer where the vectors are transformed into something richer. So at the end of this whole feed-forward network, would have a new hidden state representation or a new vector representation of each token in the sentence. Now, is this feed-forward network relevant? From experience and from research, yes. Not adding this feed-forward network to the transformer architecture drops the performance significantly. In fact, in models that are so big, we realize that the feed-forward network might even be more important than the attention mechanism calculations at some levels in the LLM's architecture. So again, the feed-forward network is simply a matrix transformation or a vector transformation of the hidden states gotten after the attention calculation. Is anybody confused? No one is confused. So I'm going to go on. Okay, so let's talk about something. Let's talk about something very important. Again, this is like a summary. You can see a diagram on the left just to keep track of where we are and where we are going. This is like a transformer block again. Once again, you get the inputs here. The inputs are converted to a word embedding. Then we add the positional encoding to that word embedding, and that is propagated into the transformer block. Inside this transformer block, we calculate the attention between tokens to get the relationships between tokens. And then when we get the output, what usually happens is that we take the input before that attention mechanism calculation and add it to the output of the attention mechanisms calculation. I'll take that again. What typically happens in the transformer block architecture is that at the two places, two layers, which is the multi-head attention at the, which you can see here, this is a multi-head attention layer, and the position, the feed-forward layer. We will take the input before the input that is passed into that multi-head attention or into the feed-forward attention, and we will add it to the output of the multi-head attention or the feed-forward attention. So if you look at this diagram, you will see that, just look at the red line, you can see that the input flows from input into the transformer block. And at this point, you can see that if you track it, we are adding it back to the output of the multi-head attention layer. Then we do the same thing again. We follow this, we pass it to the feed-forward layer, we get an output. But then we also take the input that was passed to the feed-forward layer, and then we add this back to the output of the feed-forward layer. This design or this flow is what we call residual connections, right? Residual connections. Now, what is the importance of residual connection? It helps to prevent the vanishing gradient problems that we saw in the recurrent neural networks. We found that as the LLMs grew really big, if we did not add a residual connection, which as you can see is this, the model suffers from the vanishing gradient problem. So what do? We added back, we created these residual connections where we add the inputs of the multi-head attention. We add the inputs to the multi-head attention to the output of the multi-head attention. We do the same thing for the feed-forward layer. We add the input of the feed-forward layer to the output of the feed-forward layer. So this helps the training to be stable. This prevents the vanishing gradient problems and ensures that every single layer in the large language model architecture learns something. So every layer learns because of this residual connection, every layer learns, right? So this is more of a mathematical idea than a conceptual idea, because LLMs are really big and deep. Because LLMs are really big and deep, we created these residual connections to ensure that during training they don't suffer from vanishing gradient problems, and that during training they learn better. Without the residual connections, when you are training an LLM, you will not get good results. The results will be poor. Why? Because of the vanishing gradient problem. So that is why the residual connections were created. Again, what is this residual connection? We are simply adding the input to a particular layer back into the output of that layer. So in this case, we take the input to the multi-head attention and add it back. You can see we're adding it back here to the output of the multi-head attention layer. We do the same thing for the feed-forward layer. So that is residual connections. Okay, so let's go to the one that somebody was asking about, the layer normalization. Now, I'm not going to, because somebody's head wants to blow, we won't go into the mathematics of this. But again, this is another mathematical concept that we found based on research and experience to enable the LLMs be more capable in learning the different patterns in text data or in whatever modality that they are being used. Now, if you look at the diagram below, you will see again that this is the transformer block, the decoder. Again, we have the input flowing to the attention layer. From there, we have this recurrent, you can see the recurrent connection where the input to the attention layer is added back to the output of the attention layer. Now, this output of this addition, you see here, it flows into a layer normalization layer, which transforms the layer normalization layer, it transforms the output of the attention layer and then passes it again to maybe a new attention layer or to a feed forward attention layer, as you would see here. So the feed forward attention layer, as you would see here. So you get this residual connection. By now, nobody should be confused about residual connection concepts. Residual connection, we're adding the inputs back into the output. Now, what is the work of these layer normalization layers that you are seeing here? They simply help us stabilize training. Now, what does it do? It simply recenters and rescales the data. That's all I can say. It recenters. If you know statistical machine learning, you should be familiar with rescaling and centralization, where you try to centralize the distribution and make it to have a mean of zero, yes, a mean of 0 and a standard deviation of 1. That's uniform distribution. So if you're familiar, if you cannot remember it, please go back to the lessons from last week. I'm sure it's there. Again, what the layer normalization does is that it tries to stabilize the training of LLMs. How? It rescales its inputs and recenters the inputs. Then it passes it to the next layer after it. That is all it is doing. I have left you with the mathematical formula here. If you are interested, you can learn it. If you're not interested, please, I can tell you with my full chest that you don't need to learn it or memorize anything. You just need to understand it as a concept that it helps training stable. Yes, it helps training to become more stable by recentralizing the data and rescaling the inputs. That's all the layer normalization does. That's why it's called layer normalization. It normalizes its inputs. Simple. Last one. So let's move on. Okay, now we are at the final unit of the transformer block. Again, we started with the input. From the input, we went into the embedding layer. And from the embedding layer, we went into the attention layer. Now we are at the output. Again, you will see another diagram here. This is the tokens. Remember, we said that the tokens are converted into integers. So integer 1, 2, 3, 4, 5. Through the embedding layer, we get token embeddings, which are the token embeddings are just vector representations, as we saw. What am I doing? I think I've seen all this. Yeah. So the token embeddings are simply vector representations, as we saw. How do we get the token embeddings? We will take this position 1. We will go to the embedding layer, which is a lookup table, and we will get the row at that position 1. That will become the vector representation for this particular token. So we keep doing that for every token in a sentence. Don't forget that. Now, after we've gotten the token embeddings for each of those tokens, we will then add that positional information I spoke about that gives the model an idea into the position of the tokens in the sentence. Is this in the first position? Is it at the last? Is this in the middle? Is the word at the beginning? Is the word at the 75th percentile? Blah, blah, blah. That is what the positional encoding does. Now, after we've added the positional encoding vector representation to the token embeddings, we get a new token embedding. Now, it is this token embedding that we would use to calculate the attention, right? Then after the attention, again, we have, remember, the output of the attention will be passed to a feed-forward network, and the output of the feed-forward network would finally be passed to a linear layer. Now, this is a very simplified diagram of the transformer architecture. Don't forget, we usually have a layer normalization layer, and then the residual connections. But this is very simple, just to break down and make it more easy to understand. All those things are there. They were just skipped. Okay, so after the feed-forward layer is the output layer. So this block here, you're seeing that has linear written in it, is the output layer. And what the output layer does is that it is the output layer that is responsible for predicting the next token in a transformer. Now, don't forget that in residual connections, no. So in residual connections, we are not calculating the objective function. We are simply adding the inputs to a layer to the output of that layer. That's what we are doing. There's no objective function. It's a mathematical operation, and that operation is a simple addition. That's all. We add the inputs to a layer to the output of that same layer. That's what we are doing. So now back to this output head. What it does is it predicts the next token. Don't forget that the essence of the transformer model is to model text generation. How can we generate the next token or the next word in a sentence if we've been given the previous words that come before it? So I am, if I give a model I am, how can we generate the next word, which is playing? And how can we generate the next word after that, which is football? So I am playing football. So that is what the output head does. The output head tries to predict the next word given the others. So that's the essence. So after we have done the attention that calculates the contextual relationship between tokens, we then pass this new representation of the tokens to the output head. This output head will then determine, based on that, what is the most likely word to come next. Is it playing? Is it eating? Is it football? So it determines the next word to come up in the sentence in this input sequence. I hope that is clear. Now, how does it do it? It does it by simply predicting the probabilities of every word that existed in our lookup dictionary. In case you've forgotten what lookup dictionary is, remember when I was talking about the embedding layer and I said it is a matrix? Or when I was talking about the tokenization and I said that there's a dictionary table where we convert words to integers, right? Now, imagine that we now have this output head that now tries to predict the right word in that dictionary table. That's all this output head tries to do. It tries to predict the next token in an input sequence by predicting the probability of each word in that our dictionary. So let's say we had 5 words in our dictionary. You know? In our case, I am a student. We had 4 words in our dictionary. What the output will do is it will say, okay, what is the probability that the next word is the word I? You say, well, it's a 0.02. Okay, what is the probability that the next word is am? It's a 0.04. What is the next word? What's the probability that the next word is the probability A? It's 0.1. What is the probability that the next word is the word student? Is a probability of 0.002. All right, so that's what it does. It predicts the probability for every single word in our dictionary lookup table. So you might be asking me the very important question: if it's providing the probabilities for every single word in our dictionary, how does it now determine the right word to pick? It's very simple. The word with the highest probability becomes the most likely text or the most likely token that is generated. Right? So again, the output head calculates the probabilities for every single word in our dictionary lookup table, and we then use this probability to determine the next word. So look at this generation of probabilities as a probability distribution. Again, I'm slipping into mathematics. I won't slip again, I promise. If you get what I've said, let me hear you say I. Okay, so nobody said I. I'm just going to continue because nobody said I. Okay, so that's the end of the whole transformer block. So we are done with the mathematics, I assure you. These slides will be available for you to go over to help you understand. But let's try again. I'll try and summarize the transformer block again. Right? So let's go. Again, we have the input tokens. The input tokens are converted into embeddings. Each token is converted into an embedding through an embedding layer. Now, after this conversion, a positional information is added to each of those embeddings to determine the position of the token in that input sequence. Now, this positional information is added to the input embeddings, the token embeddings. Now, after it is added, it is taken into a transformer block. Good. Now, what is this transformer block made up of again? It is made up of a layer normalization, a linear layer, multi-head attention, linear layer, layer norm, feed-forward layers. Now, if you notice, I never spoke about this linear layer in the past, right? It turns out that the transformer architecture has existed since 2017. And between 2017 and 2025, people have been trying different things that have worked and may not have worked. So this diagram, my friend, is one of the examples of somebody trying to put a linear layer in between a layer normalization and multi-head attention. Right? So I never spoke about this. Just know that people have tried different things, different new designs, adding new layers, adding new techniques to see if it improves the performance of the transformer layer. A lot of them have failed. To be very honest, GPT-5 just failed that test again. But let's not talk about this. Class is not about GPT-5. It's about transformers. Okay, so again, input embedding, we add positional information to this. Then the result of that is passed to the transformer block, which consists of the layer normalization, the multi-head attention, and the feed-forward network. I'm going to stick with that. Now you will see here that we've stacked multiple transformer blocks together, which is represented here. And this is what makes an LLM deep. So by stacking each transformer block one on top of the other, we have introduced a new complexity to the predictive capability of LLMs. And this is the single reason why LLMs can be as big as 1 billion parameters or 1 trillion parameters, because we simply have stacked a lot of transformer blocks one on top of the other, right? What is a transformer block? You can see that they've projected out to you what a transformer block is, and we've spoken about each of these modules: the multi-head attention, the layer norm, and the feed forward. Now, after the last transformer block, we will get a final layer normalization. Again, a lot of researchers keep this layer normalization. They don't use it, but some people use it, depending on if it works for them. I'm sure GPT-5 used it. That's why their model sucks. Now, after this transformer block, it is passed to the linear layer, which finally does the probability prediction. I hope nobody is confused so far. Or would you like me to take that again? Is the yes, take that again, or yes, I understand. Okay, so all right, I'll take it again. So let me start. We've discussed the transformer block, and we stated that the transformer block consists of layer normalization, multi-head attention, layer normalization, residual connections, and a feed-forward layer, right? So this diagram represents how the input flows through the transformer or the LLM architecture till we predict the next word. So starting from the base, at the base we get the input tokens. The input tokens are converted into integers, right? Like I said, based on a dictionary lookup table. The input integers are then converted to, each of them are converted to a vector representation. That representation implicitly contains the meaning of that token, right? Now it's converted to a vector representation by the embedding layer. The output of that embedding layer, which is a vector representation, is added to the output of the positional encoder. The positional encoder basically adds information about the position of a token in an input sequence. That's all it does, right? So we're trying to give our vector representations more meaning by adding its position in the input sequence to the meaning of the word itself or the meaning of the token itself. That's how to conceptualize these things. Now, the result of this addition is passed to the transformer block. And what starts in the transformer block is this residual connection, which you can see here. So it's passed to the transformer block. So the input flows like this to the layer normalization layer. Like I said, I'm going to skip this linear layer because it's not important. From the layer normalization layer, we go into the multi-head attention layer. And after the multi-attention layer, you see that there's a residual connection from here that adds the input of the layer normalization back to the output of the multi-head attention. Then the result of this addition is passed again to a layer normalization layer, which is then the output of this layer normalization is passed to a feed-forward network layer. Again, we have a residual connection that adds the input to that feed-forward layer to the output of the feed-forward layer. Now, the result is propagated to the next transformer block. So we keep propagating the result of each transformer block to the next transformer block until we get to this final transformer block. After this final transformer block, we pass the result to a layer normalization layer. Then after that, it flows again to a linear layer. Now, this linear layer that is the output head, like I explained before, it is the output head, and is responsible for predicting the probabilities of the next word given the previous words in the input sequence. So this is the summary of the flow of the inputs down to the predictions of words in the transformer layer. If you are still confused at this point, see me in my office. Okay, so now we've discussed the transformer block. We've discussed the transformer block itself. We've discussed the fundamental unit of the LLMs that we know, which is really a transformer. We've mentioned all the fundamental units that are found in the transformer block: input embeddings, positional embeddings, layer normalization, multi-head attention calculation, layer normalization, feed-forward layer, and the output head. Now, what can we actually do with this transformer block? It turns out that we can do a lot of things. It turns out that with this transformer block, we've been able to create 3 different new designs. Let's put it like that. 3 different new designs. Now, the first one is called an encoder-only transformer. Right? What it means is going to be difficult to explain, but let's look at this image on the right. I'll do my best. You're already familiar with the inputs, the positional inputs. So this positional input here is the positional embedding. The normalization layer is the layer normalization layer that you already know. So layer normalization and batch normalization are not the same, right? The normalization here is for that layer. In batch normalization, it is the batch that is being normalized. Don't worry, it's beyond the scope of this class. But what you need to know is that layer normalization is not really the same as batch normalization. In the transformer block, we have layer normalization, not batch normalization. All right. In batch normalization, you are trying to center the inputs. You try to center and normalize the inputs, but the layer normalization is slightly different. It has learnable parameters, but let's not go into it, right? So they are different. Now, but with this transformer block that you know, like I said, they came up with 3 new designs. The first one is called the encoder only transformer. The second one is called the decoder-only transformer, and the third one is called the encoder-decoder transformer. Now, what happens in the encoder-only transformer? It turns out that if we are doing attention, if we are calculating attention, let me see. Let me see. Hold on, let me see if I can get. Yes, so let's use this. It turns out that if once we are calculating attention, so I'm trying to explain the fundamental difference between an encoder-only transformer and a decoder-only transformer. Right. It turns out that when we are calculating attention, we can give it a sentence, right? We can give the model a sentence and mask out some of the tokens in that sentence such that the model cannot see it when it's trying to calculate attention. So for example, when we are trying to calculate the next word after D, this token D, we will mask out the tokens quick to the token lazy. We'll mask it out so that the model cannot see it. And then we'll force the model to only generate the next token given the token D. Now, let's say the model has generated the token, the next token as quick. So now we now have the token D and quick. Again, we'll mask out the tokens brown to token lazy, right? And force the model to use only these two tokens to try and predict the next word, which in our case is brown, right? So when it's calculating attention, it only calculates the attention between D, the word D, and the word quick. So when it wants to get the probability for the next word, it will only calculate attention between the words that come before that word we're trying to predict. So again, let's say we're trying to generate the next word after the words the quick brown fox. So let's say we're trying to predict jumps. We will calculate attention only between the quick brown fox, right? And we will use that attention mechanism to predict the most likely word that comes after fox. In our case, it is jumps. So this is called masking. During training, because we want the model to learn how to predict jumps after it has seen the quick brown fox, we will mask out the words jump over the lazy. By masking it out, the model will never calculate attention for these words jumps over the and lazy. It will only calculate attention between the words the quick brown fox and use that attention weight to predict the next likely word, which in our case is jumps. I hope I've not confused anybody. So during training, we force a model not to see the future, such that if it wants to generate the most likely next token, it can only calculate attention for the previous tokens that came before it. Right? This process is called masking. We are basically masking all the future tokens so that we are forcing the model to learn attention. We are forcing the model to learn relationships between words without looking at the future. Now, it is this masking that differentiates the encoder model from the decoder model fundamentally. So in the decoder model, we are forcing the model not to see the future tokens that exist. We are just forcing the model to say, okay, I've given you 3 words. So use these 3 words to generate the 4th word. I'm not going to show you what that 4th word is. I'm not going to show you what that 5th word is. I'm not going to show you what that 6th word is. I'm going to mask it out so that you don't calculate any attention for them. So use these 3 words to tell me what the 4th word is. That's what the decoder only model does. Now, the encoder only model doesn't do that. In the encoder only model, I will give it all the words and just say, you know what, I want you to understand language. So take all the words, calculate all the attention between every word in the input sequence, and just give me a very rich representation of what each of these words would mean. So the fundamental difference is in decoder only models, we force the model to not see future tokens when it's trying to predict the most likely next word. In encoder only models, we do not put that constraint. We allow the model see every token at once and try to get very good understanding of the relationship between words and get really good meanings for each of the words in the input sequence. So that's the difference. Now the encoder decoder only model then combines these two things together to give us, so this is it, as you can see here. So at this point where we have the multi-attention head, because it's an encoder only model, we will allow it to see all the input sequence at once so that it can get good meaning of each of the tokens in that sequence. Right now, encoder only models are typically used for tasks like classification, like for example, sentiment analysis, where we'll give them, we'll say, okay, take this sentence, tell me whether the sentiment in the sentence is neutral or is positive or is negative, right? Or take the sentence, I want you to label each word in this sentence with the appropriate part of speech. So tell me that this word here is a noun, tell me that this word here is a verb, tell me that this word here is an adjective. So encoder only models are typically used to understand language. They're not usually used to predict the next word in a sequence. So if you want to understand language, use the encoder only models. Why? Because we don't mask out anything. We allow the model see we allow the model see the whole sentence and tell it, okay, I want you to understand this language and tell me what you think about the part of speech. Is it a noun? Is it a verb? Let me classify the sentence. Is it a neutral sentence? Is it a positive sentence? Is it a negative sentence? So that's what we are doing with encoder only models. Now for decoder only models, we use decoder only models to predict. They are typically used to predict the next token or the next word for simplicity in an input sequence. Now, so all the large language models that you know now, the ChatGPT, the Gemini, the Qwen, the DeepSeek, all of them are decoder only models, and you would find them here. They are decoder only models because they regressively predict the next token based on the past tokens. So we do not allow it to see the future tokens. We give it a set of tokens and say, see, you will not know what is coming after this token. I want you to generate the next word that's going to come after these 4 tokens I've given you, which is different from giving the model all the tokens at once to understand the language. So again, encoder only models are used for language understanding. Decoder only models are used for text generation to predict the most likely next token. That's the difference. So all LLMs that you know right now that are popular are decoder only models. We won't talk a lot about the encoder only models, and the reason is simple because the encoder decoder, we won't talk about the encoder decoder models because it's beyond the scope of the class. That's one. Secondly, it's a combination of an encoder and the decoder architecture. Remember, the encoder model and the decoder model are both transformers. The only difference is that for one, we don't allow you to see future tokens, and for the other, we say see everything and come up with good representations for every single word in this sequence. That's the fundamental difference. One is used for language understanding, the other one is used for text generation. Okay, now we've covered the fundamental background of the transformer, the parts, the different kinds of transformers that we have. Now let's go into what is happening in a few minutes. Let's just talk about the basic things happening in the world now, in the innovation space. Okay, so like I said earlier, I said that between 2017, when the transformer architecture was discovered, to 2025, people have been coming out with different ideas, different tweaks to the transformer architecture, different additions, things. They're coming up with things to make the model better, to make its learning capability be better, to make its efficiency or its speed of text generation faster. And this has led to different innovations in the space. I know you guys are familiar with DeepSeek that trained their models at a very cheaper rate compared with other state-of-the-art models. Okay, so the first thing we'll talk about is one of the key innovations is the KV caching. I don't think we should even talk about this because of time. Okay, let me see if I can do this. Now, when we're talking about the transformer block, I mentioned that for every token, A key vector will be calculated, a query vector will be calculated, and a value vector will be calculated. Now imagine that every time that I wanted to predict the next token, I always have to calculate the key vector, the query vector, and the value vector for the tokens that I already seen. It doesn't make any sense, right? So every time I want to generate the next token, I will calculate key vector, calculate query vector, calculate value vector for every single token in my input sequence. That's going to cost a lot of computation, which is going to cost a lot of time. So people came up with the idea and said, you know what? I don't want to always calculate the key and value vector every time I want to calculate the next word, the most likely word. What will I do? I will simply reuse my key and value vectors from my previous iteration. So once I have calculated the key vector and the value vector for a token, I will not calculate it again. Instead, I will just save that key vector and value vector in a cache system, like a storage system. So if I ever need it, all I need to do is go to my cache system and pull out that key vector, which is faster than trying to compute the key vector and value vector all the time. So the only thing I will now be computing is my query vector. I hope that makes sense. So by doing this, they found it to be so efficient that it cuts down the amount of computations that happens in a transformer architecture, because trust me, it is quadratic. The complexity is quadratic. The transformers calculate a lot. They spend a lot of time calculating. So by simply storing the key and value vectors once they are calculated for any token, it means that we will never calculate them again until we finish our text generation, right? So that way they were able to save compute. So that was one of the key innovations. I think this happened in maybe 2020. Oh no, maybe 2019. I'm not sure. So this saved computation and time. So we got LLMs to generate words faster because we were no longer computing so much. We were storing instead of computing. So LLMs were generating really fast. So that's the first innovation. The second innovation was the rotary positional embedding. Now, the rotary, we spoke about positional encoding previously, where I said we are simply adding information about the order of the tokens in a sequence. So, to improve on that, they developed a rotary positional embedding system. In this system, we are using pure mathematics. We're not learning anything, we're not learning any weights. We're just using pure mathematics to come up with angular vectors. See, just memorize what I'm saying. If you have any questions, meet Zion, don't meet me, because it gives me a headache just talking about rotary positional embedding, right? But the major thing is these positional embeddings, the previous positional embeddings I mentioned to you guys, they are weight vectors. And because they are weight vectors, it means that they are learned during training. Do you understand? So they are put in the model, and the model learns what those weights should be during training. So what happens when we train a model for a context length of, we train the model on sentences that have just 20 words? What happens when we now want the model to generate sentences that are as long as 200 words? We found out that while we were using the positional encoding, which I described earlier, the models failed significantly. So after the generated 20 words, we saw that there was a significant drop in performance. The model was no longer generating the most probable words as accurate as it was doing in the past. So the whole research community came up with the rotary positional embedding, which is not a weight vector that is learned during training. It is just mathematics. We are simply calculating an angular vector for every single token embedding. I'm not going to go too deep into this, but all you need to know is that rotary positional embeddings, which is abbreviated as ROPE, are not learned. So during training, because they are not learned, it means that even when you are trying to generate words generate sentences as long as 1,000 words, it makes no difference. There's no difference because we did not learn it. We did not learn it during training, and because we did not learn it during training, it means that even outside training, we will just keep generating text and doing really accurate work. Okay, so the next thing was the attention mechanism. People now try to also tweak the attention mechanism by trying to do to save the not just compute space now. They were trying to save RAM. They're trying to save the memory that is being used for the calculation of the the attention mechanism. Right now, remember when I said that every token would have a key vector, a query vector, and a value vector? Well, after a lot of thinking, some AI researchers came up and said, you know what? We will not make every token have a key. So you can see that here we have 1, 2, 3, 4, 5, 6, 7, 8 tokens. So they came up and said, you know what? We will no longer make each token have a key vector, a value vector, and a query vector. They said, we're not doing that again. It's too expensive. We're using too much RAM. We're computing too much. How about we break it down and say, okay, we will make all the tokens have, each of them to have a query vector, but all of them will share the same key vector and the same value vector. Don't ask me about the mathematics, just understand the concept. So you know, said, wow, this might work. Oh. So what did they do? They created a new model architecture where all the tokens in an input sequence will use the same key vector, and all the tokens will make use of the same value vector, but the query vectors will be different, like you can see in this image. And they called this multi-query attention, right? The traditional one that you know is where each of the tokens will have their own unique query vector, their own unique key vector, and their own unique value vector. But in the multi-query attention, all of them will share the same value vector and the same key vector. So by doing this, you can already see that because we have less vectors, you can already see that we are saving RAM, we are saving memory, right? Because we have less vector to keep in memory when we are calculating the attention mechanism. So this was another invention. But they found out that when we compared this multi-query attention to the traditional attention mechanism that I discussed earlier, it performed significantly worse. So in the end, there was a trade-off. We saved memory, right? But the performance dropped. So that was another key innovation. Then after this came the group query attention. Now in the group query attention, we say, okay, you know what? Let us give each token, as you can see in this diagram on the lower right, let us give each token a unique query. But then we will now group tokens into specific blocks and give each group a unique key and give each block a unique value. So you can see that in the traditional one, each token had a query vector, a key vector, and a value vector. But in this new system, each token had a unique query vector, but their key vectors were grouped. So you can see here that the first two vectors are sharing the same key vector and the same value vector, while the last two tokens, as you can see, are sharing the same key vector and the same value vector. They called this one grouped query attention. Why? Because we are grouping the keys, we are grouping queries, we are grouping tokens, we are grouping the queries into key and value blocks. I hope that makes some sense. Now, this worked a lot better. It worked significantly better than the multi-query attention. But again, it didn't do the difference in performance between the traditional attention mechanism and the group query attention mechanism was just little. So there was significant improvement in this with this innovation. The next one was created by DeepSeek, and it is called, okay, before we talk about that, okay, let me skip this. I don't want to talk about it. So the next one was created by DeepSeek, and it is called MLA. So this is another attention mechanism. In this attention mechanism, they did something slightly different. They said, okay, people have been grouping key and value. We're not going to group anything. What we do is for every key and value pair for each of our tokens, we will transform it into a smaller latent dimension. So let's say that the original key value pair had 12 elements in their vector representation. What MLA does will now say, you know what, that 12 elements vector, I'm going to transform it to 3 elements vector. Now, it is that 3 elements vector that I will save in my cache for every token. So they are basically compressing the key and value vectors of each tokens into a smaller dimension and saving it in a cache. By doing this, they have saved RAM significantly. But that's not all they did. Then they then added a new matrix that tries to convert that latent dimension vector into its original key and value vector. So we have, like, we're encoding the key value vectors into smaller dimensions, and then we are projecting them back into the original dimension space. So by doing this, we can see that we've added one more compute. We scale the key and value vectors to a smaller dimension, and then we scale them back up to the original dimension. But we save a lot of RAM in the process, because now all we need to save in our cache system, our storage system, when we are doing the KV caching, is the smaller latent dimension vector. And then when we are trying to do attention mechanism, just before we do attention mechanism, we will take the key, this latent vector from the cache, and then we project them back to the original key value vectors before we calculate attention. I hope that makes some sense. So instead of just doing attention between key and value using the original key value vectors, we will first compress them into a small dimension, save it in the cache. Right? So the next time we want to make use of that particular token, we will not recompute the original key vectors. We instead go to our cache, pick up the latent dimension, and then project them back to the original key vector and value vector. That way, we save RAM with a trade-off of extra compute, but it's not so significant. Now, what they found is that this MLA attention mechanism performs really, really, really close to the traditional attention mechanism, and performed way better than the group query attention mechanism. In fact, it saved, according to their paper, it saved them about 93% RAM. So that's a significant savings in the memory space. So this was another good innovation by them. The last one we are going to talk about is, I think, is a mixture of experts, right? Because of time. Now, they were trying to look for extra ways to add complexity to the transformer block. So what did they say? They said that instead of creating, if you remember the feed-forward network, let me see if I can go back. Remember the feed-forward network? Where is it? Yes. So this was a feed-forward network, right? Now, instead of having this feed-forward network, what if you could have, at this particular level in the transformer block, instead of having just one feed-forward network system, what if we could have more than one? Maybe what if we had 2 or 3 or 4 or 5 or 6, right? And when we have this, we would then put something to route between each of these feed-forward networks. So that is exactly what was done here. So if you see in this diagram right now, you would see that this diagram doesn't really explain much. Trying to look for really good. Exactly, this one does it well. So imagine this 1, 2, 1, 2, 3, 4 are like the feed-forward networks in the transformer block. These are the feed-forward networks in the transformer block. So we've simply replaced the one feed-forward network with several feed-forward networks. Now, after we calculate the transformer, the attention between tokens or between words, we get this resulting inputs, this hidden inputs. That's what this input hidden represents. It represents the output of the attention mechanism block. After we've gotten this input, we will first pass it to a router network. This router network will now determine which feed-forward network that will process the output of the attention mechanism. So again, I'll take that. Once we've gotten the output of the attention mechanism, in this diagram, this input hidden represents the output of the attention mechanism. It will be passed to a router network. That router network will determine the feed-forward network to call, the feed-forward network through which this output should go through, right? Now, this router network also uses like an attention system too, where we get some weights. If the weight for any feed-forward network is low, it means do not use it so much. If the weight for that any feed-forward network is high, it means okay, we want this input to carry, it should be processed by that network. Now, each of these feed-forward networks were called experts. So an expert feed-forward network, another expert feed-forward network, another expert feed-forward network, and so on and so forth. And this was called a router. So it is because of this router and expert system that this was called a mixture of experts. So instead of having just one feed-forward network, we now have several, and then we're using a router to route the output of the attention layer through this expert feed-forward network to get a final result. I do not know who developed this. I've forgotten who developed this. Most likely it's the Mistral, but it was a very good development and innovation, and it ended up saving the whole compute world, saving the AI community a lot of compute or a lot of memory. Why? Because by using experts, we can scale a model to the top, and we can scale the model to be as big as possible while also reducing the RAM requirements when we are trying to generate text. If you need extra information on that, you can get the slide and read it. I think that will be all for now. Let me briefly use just 2-3 minutes to discuss what has happened since 2017. So now we've spoken about the innovations that have happened after the development of the transformer block. Now, these innovations have led to the different models that we now know, starting from GPT to GPT-1, GPT-2, GPT-3, to GPT-J, to ChatGPT, to Gemini, and so on and so forth. All these models have the same fundamental architecture, which is the transformer block, with just little tweaks. Now, if you look at the right, you will see that essentially the GPT architecture is about the same as the GPT-J architecture. The fundamental difference is that the GPT architecture makes use of a positional embedding. The GPT-J architecture makes use of the rotary positional embedding. So just a little tweak, and we have a new kind of architecture, right? Another difference is we are passing the inputs through the multi-head attention and the feed-forward attention at the same time, and we are adding the results together. Unlike here, where we just keep going up and up, it is just one way from mask attention to the feed-forward neural network. So people started trying new innovations, incorporating the KV caching and all those things, the mixture of experts and all those things. So if you keep going in the slides, I've left diagrams for you just showing these tweaks and how they affect the different models that you know. Here you can see Gemma and Mistral. You can see the architectures of these two models if you want to. There's also the one for Llama 3 almost. So they're just different architectures that you can see and play with if you're interested in coding them from scratch. If you're not interested, please leave them alone. Really, you shouldn't even try to do that. It's a waste of time. Right, so I think that will be all for now. Thank you very much if you have stayed to the end of this class. Yeah, that's all. If you have any questions, you can ask just briefly. Yes, you can get the slides. Let me go through the. Let me stop sharing now. Yes, you can get the slides. You can get the slides. You can get the slides. David, your questions are about. It seems like you're very obsessed with patch normalization. Please, you can send me a message. This this is going to that's going to be a long discussion. But all I can say is they've used patch normalization in the past, and not just for transformer layers. They've used it for CNNs, for convolutional neural networks, and some other neural networks, and they found layer normalization to be specifically better in the transformer model than the batch normalization model. So you don't really see batch normalization anymore in the architecture models. You see the layer normalization, which is like a tweak. Really, it's just like a tweak of the usual batch normalization, but it's just slightly different. So the whole essence of AI Summer of Code is to bring you guys up to speed on the recent AI innovations and everything happening in the AI space, right? With I think a primary focus on LLMs, and because there's a primary focus on LLMs, that's why I emphasized the decoder only transformer in this discussion. But if you're interested in going into every single aspect of the AI innovations, then of course you have to really talk about the encoder only, the decoder only, and the encoder decoder models. But again, we can't use 2 hours to discuss everything.
All right. Okay. Thank you, Mr. Jeffrey, for the informative session. Please, do we have any other further questions? Any question? Mr. Jeffrey,